All right, I will begin with a word of prayer. Soon. Heavenly Father, we thank you for this day. I thank you for these students and for the time we have to study your creation. Pray that you guide our steps today. Help the students if they're feeling discouraged in this class, that they would just persevere and do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. Amen. Okay, so graphing. Let us talk about graphing. So here more than ever, it is most unfortunate that your homework is electronic, because it really is sending the wrong message. Because we want to learn how to graph without technology. All right, in as much as you can. I mean, let me restate this. We want to learn how to graph everything that's easy to graph without technology, right? And then to recognize, okay, some things you do need technology to graph, fine, we can use that, but obviously if I'm asking you to graph something on the next test, it's because you can use the basic techniques that I'm going to share with you today and next class and class after that or so for constructing the graph, right? And these techniques I'm going to share with you, to start with, they don't really feed much into the algebra that you've already been doing, but once we get past the introductory part, we're going to be talking about how we can use factoring and the algebraic steps like completing the square to gain insight into how to make graphs. All right, so we're going to do that. Not today, but as we go on. So I'm going to start out with a basic example, unless there's a question about something. Are there any CFARs in here? Ah, okay. I knew there's one that wasn't like the others. Are you enjoying your CFA experience? It's all right.
What do you think of Jerry Primo?
The guy today?
Jerry Primo? Oh, Prevo. I probably should.
Oh, Jerry?
Yeah. It seems dope. Okay. You love Jerry? All right. Well, very good. You guys are trying to get me into a discussion of something that's going to require editing. For that reason, I'm going to go back to the math now. So I have no comment. Example 1. So let's see here. Oh, yes, I need to come up with an example. Let's graph y equals f of x given f of x equals 2. All right, here we go. 2 minus x, and then let's say x squared minus 3. All right, in the first case, this is going to be for x less than 1, and this is going to be for x greater than or equal to 1. So we haven't done anything like this in here yet, I don't think. I don't think I did yet. This is a case-wise defined function, right? These tend to give you guys a lot of trouble. So I need to remember to do some examples of them so that, you know, you get some exposure to them before you get into trouble. I'm trying to get this thing out of the way. Well, I hope you top-hatted. Are we top-hatted?
Yes.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I need my top hat to get 24. I got 22. Who is the...
Don't forget the C.
It was, well, you've done the camera work. You have an excuse. You did it? Oh, 24. Hooray. All right. So now we've top-hatted. That makes it official. Anyway. So this is a case-wise defined function, and here's the instructions using a table of values. All right. So this method of graphing is pretty low-tech. And let's get to it. So my table of values, I'm going to put over here. All right. So I want x, I want y equals f of x. And then over here, I'm going to make the point that we put on the graph. All right. And let's see here. I will do -2, -1, 0, 1, 2, and 3. All right. All right. All right, so here we go. When we have a case-wise defined function, we have to think about which case we're in order to know which formula to use, right? So first of all, I need to calculate f of -2. Which case am I in? Fortunately, we have just got done reviewing inequalities. You know the meaning of less than and greater than. Everyone got all the less than or greater than problems completely correct on the test. So everyone has a I need to work on my sarcasm. Let's see here. Let's see here. So no, I mean, I believe in my heart you know what less than and greater than means, but what I saw on paper doesn't comport with the reality of my heart. Let's see here. Anyway, more on that later. F of -2 is what? I'm in case -2 is less than 1, right? Right? Okay, so that means we're in case this case up here, right? So I do 2 minus a -2, which we know is 4. All right. And then f of -1, what's that? We're still in, -1 is less than 1, right? So I'm still 2 minus a -1, which is 3. F of 0, I'm still in less than 1, right? So we get 2 minus 0, also known as 2. F of 1, oh, wait a minute. F of 1, which case are we in? The other case, right? So I'm going to use a different color for that one. So there we've got f of 1 is, what's the formula? X squared minus 3. So 1 squared minus 3, which is -2, right? And then f of 2, what's that? 2 squared minus 3, also known as 4 minus 3, which is 1. F of 3, we've got 3 squared minus 3, which is 9 minus 3, which is 6. All right, so this is giving me points that I would like to graph. And the points are, let's see, we got -2, 4, -1, 3, 0, 2, 1, -2, and 2, 1, and 3, and 6. These are the points on the graph, all right, that we'd like to graph. So one of the pieces of advice I should give you, you're all taking science classes, I think, right? Probably chemistry, biology, zoology, psychology, exercise science? Okay. What else? What other ologies are there? Are you a math major? Oh. So what classes are you taking? Is this it? Are you lifelong ed? Are you just taking college algebra for fun? So what other classes are you taking?
English, religion, email, unit, degree.
Wait a minute, what was the other one? Unit? What?
Unit 101.
Oh, University 101. Okay, no wonder I didn't understand that. That's not a real course. Anyway, go on. Yes. Oh, I'm sorry, did I say that? Oops. What?
I think I'm taking 7 right
7 right now. I mean, I also had to take something like that when I was like my first semester at NC State. We got put in this like transfer orientation class thing where I learned HTML. I'm still using that to this day. That's why my website looks like 1995, because that's when I learned it, and I don't have any intention of ever using frames or anything fancy. I like the retro look. Anyway, oh no, someone's going to hack my website. What would it matter? You know, I don't know. It's not secure. I don't care. Anyway, I mean, securing what? PDFs of things I want to share with people? What would that matter? Anyway, okay, so, well, I have no example for from your classes with graphing. I mean, is there graphing in, you say, evangelism?
Yeah.
Do they graph in evangelism? No. Why not? They don't care about mathematicians? Like, how are you going to understand science people if you can't graph? You should reach out to the science people. Yeah, I learned graphing. Think about it. No? Okay. I tried. So there may exist a major here where you don't graph. Although I do wonder why you're in this class if you're in such a major. Seems like 115 would have been the correct choice. But it's too late now.
Yeah.
It's too late to
Honestly,
apologize.
put me in a class. So if you're
Your advisor just put you in a class?
you can take these 3 options and this one's better, and I said, okay.
Well, it's good that you didn't take Math 115. The guy who teaches that's a jerk. Let's see here. So, what's that? I'm the only teacher of Math 115 residentially.
Oh.
So, but okay. So before I waste all of our time with inane banter, when you're making a graph, if you want to make it pretty, you need to keep in mind what's the range of the x values and the y values, right? Because like a lot of people have this bad habit of just making it 10 by 10, even when everything's happening in like a little 2 by 2 square, right? But you should choose the scaling to indicate the behavior of the graph, right? This is good graphing. You want to make it focused on what's interesting. And in this case, what I know about is between -2 and 3. So I want my x, probably I'm going to go -3 to 3 for my x, and my y values are going from like 6 down to -2. So I'm probably going to go like, I don't know, like 0 to 6 or something. Already I don't like what I did here. See, this was bad. There, I'll fix it. Okay. See, because nothing really interesting happens much in the negative. I got -2, I guess, so fine. All right. Okay, so here we go. I'll make this 3. So, let's see here, like that. So one of the things when you're freehanding a graph, you don't have to make the divisions the same up and down, you know? Like you can choose different scales on the x and the y. Now, in your test, I will have some problems where I ask you to graph, and I'll give you like a little graphing, you know, grid to draw something in on, all right? Sometimes I'll set the scale, but I might have one where you're supposed to set the scale if I'm stupid, because then I would have to grade 200 different scales in my 200 tests. So probably I'll have set the scale, but if I was dumb, I wouldn't. All right, so anyway, I think this is big enough to capture everything we're doing. And now, let's get it. So first of all, -2, 4, where is that in this picture? It's like here at -2 and at 4, so it's kind of like here-ish, roughly speaking, right? So right there.
Is it an open circle?
Nope, that's a closed circle. And then -1, 3 would be here. Okay. 0, 2, that's the y-intercept actually. So it's about here. Let's see here, then what? And then at 1, what happens at 1? F of 1 is minus 2, right? So it's like here. And then f of 2 is 2, 1. So that's like here. And f of 3 is 3, 6. So that is roughly here, right? So when you've got something that's a line, it's good practice. Get a ruler. I'm good. I've been practicing in the other classes. So that's that. There we go. So this goes on and on like so, right? But there's an open circle right here, right? Because at 1, this right here, 1 comma minus 2 reflects the fact that f of 1 is equal to minus 2, right? Because minus 1 is in the blue case. Excuse me, 1 is in the blue case. I get 1 squared minus 3, which is minus 2, right? We're in that case. So that's where I fill in the dot. That's where the function's defined. F of 1 is minus 2. And then you kind of have to use your imagination a bit here, but what's going on is like this. So these arrows at the end, that's the first time I've drawn that, I think, as far as I can remember. Maybe. I don't know. I haven't done much of that. The examples I've given you on the quiz and the test, they didn't have those, did they? They ended with an open dot or a solid dot. So now arrows, what's that mean? It means it keeps going on and on, right? So what's the range? What's the domain of this guy? What's the range of f of x? What's the domain of f of x? The domain is easy. It's everything. Everything is defined either with the first formula or the second formula. We define the value for everything. So it's just minus infinity to infinity. What's the range, though? That's interesting. A little bit more. 2 to infinity. Is 2 included or excluded? Included because of that solid dot right there.
Wait, what did you say?
Oh, did I? Yes, thank you. You guys probably said negative, and I just lost it. About half of you are still really, really shaky on this because that problem on the test did not go well. A lot of you got this wrong, this kind of problem on the test. So, just saying. Yep. But anyway, there's the graph y equals f of x. Okay? This is graphing by making a table of values. What time is it? 3:33. So it just took me about 15 minutes to make one graph, carefully. Now, if you're on paper and not making inane banter with your students, since you don't have students, but you have friends that you talk nonsense to, right? I'm sorry, you guys are totally serious. There's no nonsense in your life, right? But what? What'd I do?
I'm going to just aggressively grab the ruler.
Am I gonna have to separate you two?
Yeah.
Oh, okay.
I don't like her.
I think we'll start bringing a Nerf gun to class, and like if I don't like the behavior, I'm just gonna be like, psh. What's that?
French teacher, she threw shoes.
Through shoes?
Yeah.
Ooh.
Yeah, and then she got to the 8th grade, and then
Wow.
she got in trouble by the parents.
Really? Throwing shoes? That's hardcore. I like that.
It's dangerous.
I have put forth the idea. I was told by another professor I should stop talking about this, but I've been often intrigued by the idea of dog collars. Like we had this thing with students bringing clickers to class, and then you ask them questions and they hit the clickers, and then you could do this with the phones with the top hat, right? You can have your top hat quizzes. You guys have classes with top hat quizzes? Are they fun?
Yeah.
Okay, good. It's English? Ah. Okay, so that improves your learning experience? It makes English a game show? Kind of, sort of.
You never know when it's coming, so you kind of have to.
Oh, it's to force you to pay attention? Okay, well, but I thought, what if you had like, everybody had to wear a dog, you get in class, you wear your dog collar, it's one of those shock collars, so like, that would just raise the level, right? Like if they don't behave, you can just like you're talking in class? Oh, fine.
I would never
You know.
do anything in class. I just sit there.
No, if you don't answer, I also shock you.
Oh.
So I would be,
Like everyone can answer at the same time.
well, somebody's going to answer because otherwise everybody's going to get shocked.
So like if we raise
Trying to do a Squid Game type of math.
I have not watched the Squid Game, so I can't say, but is that what that is? For the record, I've had this idea for a decade at least.
Can't control their bladder.
Well, that would be unfortunate. I guess I'd say you probably should take a different section. Let's see here. Anyway, I think that there are various ethical boards that it won't get passed, so don't worry. Okay, so standard examples. So we need a list of standard examples so that we don't have to do this, because this is very very laborious, very clunky, right? And by the way, even graphing calculators, can graphing calculators do this?
Yeah.
They do cases?
Yeah.
Okay, good.
Just get that
So you guys do cases on your graphing calculator?
No.
Because the last section said no, you don't have graphing calculators. That is a good answer. But
Wait, so what
Hmm?
Graphic calculator.
what?
Wait, if that was what kind of example is that?
Oh, this is a graphing by table of values example. My standard examples, I mean that what I'm trying to say here is we're going to make a list of things we should just have memorized. Okay, the things I'm about to say, you need to memorize these. All right, and so here we go. Number 1, y equals mx plus b. Number 2, y equals ax squared plus bx plus c. Number 3, y equals ax cubed plus bx squared plus cx plus d. All right, I'll stop there. Let me label these. What you got? You got yourself, we already know about number 1, right? Line, parabola, cubic. Yeah. So that's their names. That's a line, that's a parabola, that's a cubic. And what do those look like? See, what I'm trying to say is you should have memorized that when you see that formula, you think this shape. All right? And so crudely speaking, I'm going to make some sort of large pictures for this. So what I'm trying to say is these pictures are only accurate in their large scale behavior. And, you know, I'm not really, well, you have to understand the spirit in which these pictures are made. So if you got a line, there's 2 cases, right? It either does this or it does that, right? Positive slope or negative slope, right? If you've got a parabola, it either opens up or it opens down, right? But roughly speaking, it looks something like this. Or it looks something like this.
What if it opens to the side?
Then it wouldn't be a parabola.
What would it be?
That would be a sideways parabola. So, I mean, okay, fine. If you want to be that way, a parabola is the locus of all points which are, you know, equidistant from a given directrix and a focal point, right? This is how we can define a parabola. It's the set of points which are equal distance from a given line and a focal point. A line is a set of points which are of equal distance from a given pair of focal points, right? A circle is a set of points which are equal distance from a center. An ellipse is a set of points where the sum of the distances from 2 focal points are held constant. A hyperbola is a set of points where the difference between the distances from 2 fixed focal points is held constant, right? We can define parabolas, ellipses, lines, circles, hyperbolas in terms of classical geometry, but we don't do that in here because this is not a geometry class. But that's the better answer to your question, what is a hyperbola? I mean, what's a parabola? Really, we should give that classical definition. See, because you said sideways, right? But they could also be rotated. There's an infinite different variety of ways parabolas could look like. And to really do the equations, the formulas justice for that, we need linear algebra because we need rotated coordinate systems. So I like his questions. They always take me to places I'm not supposed to go in college algebra. So these conversations happen in none of the other sections of college algebra.
Really?
Yes. Because they're all like, only at this time of day do students finally wake up. So, yeah. All right, so anyway, not ignoring your question, I mean, it's interesting to talk about other kinds of parabolas, but we're focused on functions, y equals f of x. So this is our context, okay? These are parabolas. There are, of course, other kinds of parabolas, absolutely.
They wouldn't be functions, though.
They would not be functions of x. So cubic looks like these, or like that. So like a snake that goes up or a snake that goes down. Again, positive, negative. So in your book, they've got some problems in the My Labs, which have questions about the quote-unquote large-scale behavior of functions. That's what I'm trying to get at right here. The large-scale behavior of a line looks kind of like that or that. The large-scale behavior of a parabola, it either opens up or it opens down, right? I am not at all committing to the graph having to cross the x-axis here. That's just coincidental in my picture. When we, yeah, just the shape. When we study this more carefully, right, we'll figure out where are the x-intercepts and where's the vertex. That's for another day. Generically speaking, though, A positive means it looks like this. A negative means it looks like that, right? A positive looks like this. A negative looks like that. So I think that's just one of the things I assume students know. I want to communicate that this is something you should just have a generic equation sense, graphic sense. If you see this, you know what you're looking for, right? Later, we're going to nuance this and find ways to polish this and make more details on the graph, right? But it's important to know what you're looking for before you find it. That keeps you on the straight and narrow, right? If you have something like, 3x squared plus 2x plus 7, you don't know where it crosses the x-axis, but you do know it looks kind of sort of like this, is my point. All right, so there's that. And now what I'm moving on to is what we'll actually tend to use going forward. So y equals x squared, 5, y equals x to the 4th. All right. What's that? You're all good. It's all good. So let me draw a picture of those. All right, so roughly speaking, and here I'll be a little bit more precise in my graph, okay? Just because I want to show you the difference between these two is all. So here is, if I was doing this carefully, I really should figure out what the halfway point is. Where does x squared go through in the halfway point? I mean, at a half or a minus a half, what is it? What is the value of the graph at minus a half or a half if we're looking at y equals x squared? What are these points right here? Where are they at? No, y equals x squared. The points are x comma x squared, right? So a half comma a half squared. A half squared is a quarter, right? So 1/4. So it's like, this should be half the distance of that, basically, if I did it right. This is y equals x squared. What does y equals x to the 4th look like? It's useful to have them both on the same graph. So I'm putting both examples in one graph here just for means of comparison. Yeah? What do you say? I just didn't hear you. I'm sorry. It's okay. Okay. So if I'm going to make y equals x to the 4th, right? When you plug in 1 or minus 1, what do you get?
1.
You get 1, right? Plus or minus 1 to the 4th power is still 1. So it's still got these 2 points, right? But what happens when you look at a half to the 4th power? What's that? 1 over 2 times 2 times 2 times 2 times 2, right? 1 over 16. So it is like tiny. It's like down here, right? Y equals x to the 4th is way, way closer to the x-axis between minus 1 and 1. And then what happens roughly speaking here.
That's not a parabola anymore?
No, it's not a parabola. I don't even know like a geometric description of y equals x to the fourth. Oops.
So,
Roughly speaking, this is y equals x to the fourth.
like a thimble.
It's more like a thimble, right? If you look at y equals x to the sixth, it looks even more like the purple thing. If you look at something like y equals x to the 10th, it looks more or less, here's minus 1 and 1. It more or less, if you just look at it, it kind of looks like this. Up to the limits of my artistry here, because it just grows so fast past 1. So they kind of like, as you go higher and higher even powers, they just kind of inflate into the edges until it eventually looks square, kind of like that. So they eventually look like goalposts, basically, right?
And it goes upwards to
Yeah, upwards to infinity both sides. But so I would just summarize by generically speaking, if you want to know what the graph of, this is y equals x to the 2n power. Roughly speaking, x to the 2n power looks like a parabola. But they're more bowl-shaped if they're higher powers, truth be told. Okay, fine. So that's examples 4 and 5. Mostly we just use x squared, all right? So I'm making really too much of a big deal about these other things. But next up, x cubed, right? Or y equals x to the 5th power. What do those look like? So generically speaking, those guys look like, let's see here, if I do the same kind of thing I just did. The cubic would go through like an eighth at the halfway point, or minus 8. So the cube is going to look something like this. And if I was so foolish as to attempt graphing the 5th power, it would be steeper past 1 and closer to the x-axis within minus 1 to 1, like that.
They would still go through the horns.
Yeah, everything still goes through. These points are fixed for all the different powers. That's true, if I did it right. These points are minus 1, and 1, 1. That's true. All of the graphs we're talking about, all odd powers of x, all odd power functions go through these pair of points, 1, 1 or minus 1. All the even power functions, go through minus 1, 1 and 1, 1. But thank you for that question. It reminded me I could give these a name. These are odd power functions. And these up here are even power functions. One of the things that I mean to mention today in all of my classes is that these are respectively even and odd graphs. What do we mean by a function being even? Even means what? F of minus x equals to f of x, right? This is an even function. An odd function, f of minus x equals to minus f of x. This is the definition of odd function. So it just so happens that an odd power function is in fact an odd function in the sense that f of minus x is equal to f of x. An even power function is also an even function in the sense that f of minus x equal to f of x, which is to say that the graph of the even functions mirrors about the y-axis, right? Whereas the graph of the odd functions, it like mirrors but flips over. So through the origin, sometimes we say, yeah.
Did you put the points that you put on the low graph, on the odd graph, and the even graph?
The points.
Yeah, the minus 1 that you put in the 1, 1 up in the...
Oh, yeah, sure. Excuse me.
And this will always be the case for every graph.
If we're just looking at x to the power n, they either go through 1, 1 and minus 1, 1, or 1, 1, and minus 1, minus 1. Yeah. Because 1 to the power plus or minus 1, or minus 1 to the power plus or minus, anyway, 1 to an even or odd power is just 1. Minus 1 to an even and odd power is either plus or minus 1. Anyway, that's it. Moving along here. 8. I make sure I don't run out of time. Uh-oh. I better get on with it. Here we have y equals the square root of x. 9, I will talk about y equals the cube root of x. 10, I will talk about y equals to the absolute value of x. 11, I will talk about y equals to 1 over x. 12, I will talk about y equals to 1 over x squared. And then we'll do an example. So I better get on with it since I've spent all my time jibber-jabbering. So let's draw the graph of each one of these guys. So what's this square root of function look like? It looks like, so you were asking me about parabolas earlier. This is half of a parabola turned sideways, right? That's actually half of a sideways parabola. If you square y equals square root of x, you get y squared equals to x, which is just a parabola with the roles of x and y reversed. It is in fact half of a sideways parabola. Y equals the cube root of x is literally the cubic graph turned on its side. Same shape, just x and y roles reversed.
Those are the sideways, huh?
Yeah. Y equals absolute value, well, this is just the v, right? Y equals minus x, y equals x. There you go. That's the absolute value function. The reciprocal function looks like this. This also shares your favorite points. It's also got the 1, 1 point on it. And down here it's got the minus 1 point on it for what it's worth. All right.
The other one's not?
You know, actually all of these graphs have those points. You're right. That's funny. I hadn't really thought about it, but you're not wrong. This point is 1, 1. 1, 1's on this graph. 1, 1's on this graph. Minus 1's on this graph. This one's got 1, 1. And this one's got minus 1, 1. All right. So some names, of course. This is square root function, right? The square root function. This is the cube root function, right? This is the absolute value function. This one I call the reciprocal function, right? Then this y equals 1 over x squared looks like this. All right, and what's my name for this one? I call this the volcano function, haha. Oh, you thought I was going to give it a proper math name. No, I just call this the volcano function because it looks like a volcano.
That one does not have the point. No.
It's not just me. This one also has 1, 1, and also minus 1, 1. It intersects the absolute value graph at those points, actually. Now, a little bit more I should tell you in terms of description. Notice that of all of these, mostly the domain of everything is what? The whole real line, right? What are the exceptions? Square root function, right? I should make a remark. Y equals to the 2nth root, which is, by the way, x to the 1 over 2n. Pretty much same. Pretty much same graph. And down here, if we look at y equals to the odd 2n plus 1th root, x to the 1 over 2n plus 1, again, same graph. Pretty remark, yeah. Yep.
For the volcano function, is it always symmetrical?
Yes, so this is actually, by the way, an odd function. And this one, by the way, is in fact an even function, which means it is symmetrical in this case, for sure. Are there volcano functions which are not even? Sure. I can show you one of those in just a second. Before I do that, one more thing. There are vertical asymptotes, right? This x equals to 0, x equals to 0. Did I actually make that?
I think you did.
Well, that's like a first. Oh, wow. Wow. That's it. I'm curving the test in here. All right, let's see here. So that was a joke. Sorry, I shouldn't take it away from you so easily. Okay, so this is a vertical asymptote, which I will abbreviate the VA. All right. There is also a horizontal asymptote, right? Y equals to 0 is a horizontal asymptote. And likewise up here, these both have vertical asymptote and horizontal asymptotes of the x and y axis. Yeah.
Would you mind defining asymptote?
Yeah.
An asymptote is something that the graph approaches, but typically doesn't cross. So the vertical asymptote, they won't cross, because to cross the vertical asymptote, you don't cross vertical asymptotes. I would just say that. Horizontal asymptotes, you can have a graph which crosses a horizontal asymptote. Like you could have a picture of a graph. This could be a horizontal asymptote. And what that means is that the function eventually gets closer and closer to that. So you could have something like this. Like that. This could be y equals f of x. It would still be the case that you have a horizontal asymptote. Maybe this is 2. There's a horizontal asymptote of 2 for this one. It just means that the graph is getting closer and closer to that line as you go.
You can't cross for a vertical one.
Because that would mean the function's infinite.
Gotcha.
Yeah. I mean, if you want to be persnickety about it, you'd be like, yes, it can. I just defined the value of the function to be 1 here. There's a function with a vertical asymptote which has a value at the vertical asymptote of 1. But for whatever reason, we don't allow this. I mean, mathematics allows it, just college algebra doesn't. So, bye. All right. These are our standard examples. What do we do with them? So once we know the standard examples, we can use those to make new graphs. Let me show you how. So you need to have these memorized in the sense that you should know without looking in a book what the graph of y equals x cubed, x squared, cube root of x, square root of x, absolute value of x, 1 over x, 1 over x squared. These are all things you should know. Right? Now, admittedly, if for some reason you forgot, you could fall back on this way of doing things, and you could figure out pretty quickly by plugging in a couple points what the shape is of any of these standard examples, right? But you shouldn't need to, because you should know them. In the same sense, like if you have a girlfriend or something and you're like, what's your name? It would be offensive, It's kind of like that here. Like these are close friends of ours. We should know their names. We should remember their names. Example 2. Y equals x squared plus 3. All right, so to graph that, here's what I do. This is y equals x squared. To get 3, I shift up 3. And I typically track a point. So my vertex was 0, 0. Now it goes up 3. And now it's at 0, 3. There's my graph. Done. This is graphing by transformation. Or, example 3, I could have y equals 2x minus 2 squared. If you take the formula and you replace x with x minus 2, this shifts the graph right 2 units. So my vertex is no longer at the origin. It's 2 units over. It's over here. 2, 0, graphed.
You don't really need the exact other points. You
It's useful to,
just the vertex.
well, I mean, you can always add detail, right? But I try to at least track the vertex to keep myself honest. Here's another one. Y equals 3 plus the EPS value of x plus 1. So this one is a little bit more complicated because it's got 2 different things going on in the formula, right? So the way I'm going to look at this is we start, what's the,
They go up 3 and 1 over 1.
yes, but the opposite, we're going to do the opposite of that, but yes. So the question is, what is the basic ingredient here? What's the standard example which this is based on? Obviously, absolute value x, right? So I start with absolute value of x. And then I'm going to shift left one, and that looks like, and so I'm going to track the origin as a means of keeping track where things are going. So 0, 0 maps over here to minus 1, 0. Now I've got y equals absolute value of x plus 1. So when we add to the argument, it's opposite. Like adding 1 shifts 1 to the left.
Your arrows to the right.
So, but I'm talking about what's going on in the graph, not what's going on the board. Let's see here. Okay, so shift left like that. And then, what's next? Add 3, right? So shift up 3. So that moves the vertex from minus 1, 0 up to minus 1, 3, like that. So there you go. That's the graph. Y equals absolute value of x plus 1 plus 3 right there. Now, if you don't follow me yet, that's fine. I'm going super fast because I'm out of time, right? But when you learn this method, you can graph pretty complicated things by starting with the standard example and doing a series of transformations to get your graph, right? In practice, this is much, much faster than this method, than our first method, right? Now, you can use a combination of these methods to produce as careful a graph as you need to, all right? But anyway, we're going to talk much more about this. I'm going to give you a list of things we can do. There's more. There's also stretching and compressing and flipping, reflecting. We need to put all these ideas together to take our standard examples and make new graphs, all right? And I'm actually going to have you guys have some graph paper that you write on physically. And we're going to do that together because writing on the board for what we're about to do is just kind of, So we're going to have an in-class example next time. You need to stop recording because I got to give you guys the test back. So I got to name names.